Thank you very much. Thank you very much to the organisers. Can I check everyone can hear me at the back? It's clear enough. Brilliant. So there's been a trend I've really noticed in this conference, and everyone's really been talking about customer centricity. And that's something which we really take to heart. And I think what we hope to demonstrate is not really our opinion, but what's come from many conversations with organizations like yourselves, executives like yourselves, or even yourselves outside in the coffee breaks, and really sort of hoping to show you how the workflows for your team can really be improved. You got the clicker? Yeah. Thank you. So I have two titles for the presentation. There's a commercial title, which is trimming out-of-pocket R&D costs, and these are really your sort of known unknowns. So the costs of failed projects, we all have some, as well as consultancy fees, analyst fees, and opportunity costs as well as your unknown unknowns, the ones which really keep us up at night. But the thing that I'm really passionate about is this whole idea of democratizing big data analysis. And some of the conversations that I've had with a few of you outside is we're looking at the technology industries, the semiconductor industry, the electronics industry, even the construction industry, and some of the analyses and their workflows are really sort of frameworks that we're hoping to bring into the chemical industry ourselves. So before I jump in, I just want to go into a little bit of a frame. So this is the R&D process that we all know and love. But the whole process, the whole concept is behind this idea that R&D productivity does need improving. And, this has been backed up by the esteemed Anne-Marie Knott, who in her latest publication indicated that R&D productivity has declined 65% over the past 3 decades, which is quite staggering given the acceleration and advancements that are available to scientists. You add that to the fact that as more and more blockbuster patents are now being expiring, there's now a movement towards product commoditization, and there are global pricing concerns, especially in typically price inelastic industries. This is really just something that we found when we're looking at the pharmaceutical industry, but that attrition rate, there is the same attrition rate, maybe not to that degree, but also in the cosmetics industries, the nutrition industries. We all have attrition rates, projects which just do not get to market. And that then leads to a very large R&D cost. And this is just from a particular study, but you of course know the costs that you have at your particular budget. So it's really how can we actually improve this idea of R&D productivity, not just at the top line, but the bottom line as well. So I think the second talk yesterday was really talking about this whole concept of the iterative cycle. If I just go back one slide, this entire process is riddled with the scientific process of essentially gathering information, understanding and then reflecting upon it, and then doing and deciding, and actually that scientific process of moving further and further, optimizing your particular substance. So the idea is that we know that this occurs. Those who come from a technical background have been involved in this. So the idea is, have we measured how often this occurs? What's the duration of those typical cycles? Who's involved, and how much does it cost? And if you can impact those metrics, that's when the productivity then increases. One thing that we do know that all really is based around the idea of answering questions. Whether it be optimizing a substance, screening, or at the project decision-making stage, it's turning that known unknown into a known known. And this is across all industries. Not whether it be the questions to how can we optimize the plastics, make it more sustainable, as we described in the nutritional space, looking at plant-based sweeteners, the pharmaceutical space as well in terms of new therapeutics, but also within the FMCG and cosmetics arena. I mean, just taking one example that we've actually been working on is actually if you, for example, have a particular protein target, really trying to figure out what existing chemical compounds or substances bind to a particular protein. Or, for example, if you're looking at sweeteners or you're looking at cosmetics, what are the applications, the toxicities? Are there any secondary uses for that particular compound? Everyone's looking for secondary revenue streams. And when you're looking at blockbuster products like ivermectin, which has found multiple uses, biocides, pharmaceuticals, and other uses, really everyone's really looking at how can we then use all the data that we're collecting, as well as all the data that's out there, to really speed up that process. So you can, of course, go in and look at patents and journals, but no one really wants to be doing that. And typically what would happen is that I think a lot of the organizations have in-house data scientist teams. This is really up and coming. And typically the scientists will then ask that particular question of the data scientists. This is the typical process in which they go through. They have a synchronization, they're discussing, scoping out the project. There's a research stage just to make sure that they're aware, and then they go and they acquire the data, they clean it, they link it together, and then they build the visualizations and the answers for that particular scientist. So from the audience, can I get 3 guesses to how long this process on average takes in a typical organization based on our studies?
4 weeks.
4 weeks?
6 months.
6 months? Do you know the answer? Because it is actually 6 months. It's a 6-month process. Given the fact that when you remember that we're talking about a scientist within the lab who's trying to push further and further and further, so that leads to either 2 things. Either this project continues, or they give up. And they just go on and they go through the same old process of reading, going through countless patents, countless journals, trying to figure out what the answer could possibly be, or taking that shot in the dark, which is often still the case. The second the second problem is actually when you're looking at it in terms of the cost basis. So those are just a few figures. So, those figures mount up, but the big one is actually, let's say that this is actually the process that then goes on. The R&D project is either stagnant or it's stalled, because you're still waiting for that sort of gate to then be pushed forward. Another problem is that actually the demand for these individuals exceeds supply. So this is a PwC survey study. They found that there's 50% greater demand for these data scientists than there is available. And you're not just competing with the Nestle's, the Pfizer's, the IFF Chemicals. You're also competing with Apple, Microsoft, and Google. And this becomes a major problem. Because then becomes a major talent drain. So I was thinking about how I can, based on all our research, based on all our conversations, our studies going into organizations and getting a sense of what the main problems are, sort of created this sort of mini company here for you. So of course, these are the different stages of the R&D process: project strategy, that's where the executives are, substance screening, substance optimization, the commercialization aspect, IP strategy, of course, sit over here, and there's the data analyst team. And typically, of course, there'll be a particular question that's asked of them. But as they're going through that 6-month process, there are more and more questions that are actually being asked. So that's everything from, is this the correct target? What's the latest plastics or polymer bases that are actually being brought out? What's our competitor? What is our particular competitor doing in the space? How toxic is this particular compound or the chemical space around this compound? And that then leads to that bottleneck. And this is a real problem. This is an existing problem in pretty much every company that I've actually had the pleasure of speaking to and working with. So there are a few solutions that have been tried. So everyone loves a decision maker. So typically they put a decision maker who decides what's the right project to go through. They then get sent a multitude of different projects, and based on importance and, of course, lobbying, then certain projects then get taken across. But all that's actually happened is actually take the bottleneck upstream. It doesn't really solve the problem. You can always do what great executives do and delegate, and this is typically what's done. And all the different departments have their own individuals who then take their projects and decide the most optimal ones. And oops, sorry, I've jumped the gun a bit there. And typically what happens is that, yes, there is a much more controlled process, but then this then becomes highly politicized as each individual division starts referring to that their problem is far greater than the other problems. So what came out of this entire study was actually the one real main solution that really helps everyone is to democratize. If you take that process and that solution capture and allow people to individually go in, ask that particular question and bring it out, what it does is it frees space for this data analyst team to actually start working on the real advanced work. A data scientist has not actually been trained to do the typical work that they're doing. That's far more, they've been trained to do the real research and development to actually really advance your company beyond your competitors. But that bottleneck has actually prevented them. So if you can take the typical questions that they've been asked, extract and clean all the data that's external to your organization, allow your organization's internal data source, your clinical trial, your trial information, your toxicity studies to actually be put in as well. You're able to then have that solution provided for your entire company. And that's really the product vision, and that's really what's really being moved for. But what's actually needed for that to be successful? So the first real thing is it needs to be accessible everywhere. Because as you're aware, you don't typically get your ideas in the lab or in the office. It's usually at home or in the shower. So it's typically being able to have that accessibility everywhere to actually log your ideas and put it in is incredibly important to people. And it has to be intuitive. Long gone are the days in which there are extensive training programs for particular software pieces. The switching costs are too great. So it needs to have that sense and feel of a business-to-customer relationship, such that anyone can go in and throw in their question and get an answer out. One of something that's incredibly important is being fueled by a diversity of data sets, not just looking at patents and journals, because essentially that's just the old days, but really bringing in toxicity information from ToxNet and HSDB, bringing in regulatory information from ECHA-REACH and the EPA, as well as the FDA as well, and then bringing in much more diverse data sets. So, for example, if you're working in the cosmetics, the cosmetics industry or the pharmaceutical industry, what we found is the traditional Chinese medicine there's a host of information out there linking active ingredients found in those. And actually, if you're able to link that information towards, then actually that may be a direction towards more novel products. We're also looking at it in terms of secondary uses. If you're working within the FMCG space, how typically do you look at the pharmaceutical industry's data? Actually, if you have a much more holistic view, you're actually getting a sense of there is actually a secondary use that you can license out your proprietary chemical to. This whole idea of surrounding chemical space was actually discussed yesterday, and this is something that's really at the core of what we found, is that typically scientists within organizations are working with chemicals that have not been published. Either they've not been published or there are hundreds to thousands of patents out there. So how can they understand the information on a chemical that's not been published by actually looking at all the chemicals that are similar to it, taking all the information and getting a sense? So, multiple data sets, and this is ever and ever growing with more and more of our customers. So everyone's here has been talking about listening to their customers. So every single data source that's actually been added in a bi-weekly basis has actually come from someone using that information and us diversifying and democratizing it out to the chemical industry. And that's had positive has had a positive impact. But then when you take that and then place the chemicals upon it and then have a much more holistic view, what you start getting in is insights. So what I'd hope to do in the remaining time is just go through an example of such a question and then answer. So for example, this is an example. It's not an exact example, but something that has actually occurred. So this is a proprietary chemical, and it has not been published. It's not within our database or any database that we've found. And so there's no patents or journals that have indicated it. So actually, once going in, you actually want to get a sense of, all right, what information can I get about this particular chemical? Is this a pharmaceutical chemical, cosmetics? Is this, what properties can I get? If there are any journals or patents attached to it, I frankly don't want to read through those patents. Give me the information as quickly as you can. So when you put that in, and you get certain chemicals which are within 0.84 points of similarity, then you're actually looking at it that the nearest one is rivaroxaban. Now, sure, there are patents that have claimed rivaroxaban or have mentioned rivaroxaban, but no one wants to be reading through those patents. It usually takes typically about 5 hours to go through 100 patents. And here, there's 411. There's not enough time for a scientist to go through that, given that they've got an entire project. So getting a sense of immediately that, yes, rivaroxaban is near, but within those patents, these are the main concepts. It's a factor X, it's a factor XA inhibitor. It's a coagulate, and it's related to a coagulation factor. And in fact, rivaroxaban is an anticoagulant. I haven't done anything to this. That's just the information that's found within those documents that's extracted based on their importance. And if you, for example, put in purpose or target or taste or color, actually this then morphs this to look at the information that's surrounding those words. So what it means is that, yes, you can then go in and read through the journals, but it allows people to get a sense of the information as a whole. Something that in yesterday's keynote speech was mentioning that that the way that the human brain is conditioned is to bring in multiple different concepts, put them all together, and then dig deeper into it. You can then look at it in terms of actually, let's just look at the most prominent chemical compounds in there, and then getting a sense of how they compare. So there's a particular cosmetics company, a very large one, and what they've found is that they're typically using, they're doing searches of multiple different derivatives with different properties. So how can you understand the differences between the properties of very similar compounds as quickly as possible? Once you dig deeper into these, it's not just information in terms of the journals, but actually information in terms of therapeutic uses, ADME properties, toxicity information, not just human toxicity or non-human toxicity, but environmental toxicity as well. There's been a huge case for sustainability and environmental protection here in this conference. And this is being added more and more based on the information that our users are looking at. But when you go in, the real main problem that we found, and it really goes towards this whole idea of landscaping, is that yes, these are all similar to one another, but there's a degree of relativity. When you're looking at chemical space, everyone's idea of real chemical space is more of a 3D view. Because because this will be different from this, then this is different from that one and this from this one. So how do you get a visualization of all that information in one go? Longer the days in which you're looking through tables of patents and journals. So we created what we call the chemical landscape. So what you're looking at here are the chemicals that were within that table. And they're arranged based on their similarities to one another, their structural similarities, not skewed at all, purely chemistry. So what happens is that this is our proprietary chemical. I don't know whether you can see it there, but that's it there in blue. There's no patents. It's not been patented. And, the chemicals, each bar is a chemical, and the chemicals that are around it are more similar than the chemicals that are further away. So this is looking at the one that's further away. This is looking at the one that's nearest, rivaroxaban. So actually you're getting a sense of what's the competitive space around it? There's no chemicals that are directly next to it in terms of publications, but you can see that there is a highly claimed chemical compound over there, rivaroxaban, and actually further away there's also a chemical island that's found here. When you're looking at patents, your organizations are filing Marcuse structures. You're actually filing the chemical space that is actually around your proprietary chemicals. So how can you get a sense of that chemical space around it and ask questions of it? So when it comes to asking questions, one question that is always asked is, am I in a new area of chemistry or am I in an old area of chemistry? So everything in yellow is everything that's from 2005 to 2010 in terms of publications. Everything in blue is 2010, 2015, and then everything in red is past 2 years. And what you can see is that you're getting a sense of there are areas of chemistry that have not been published in or have not been claimed in now a decade. And this is typical pretty much all chemistry. You actually get islands which have not been patented for a while, and then they've essentially migrated to an optimized structure. So are you able to then get that visualization, get a sense of how has someone optimized this area of chemistry for their purpose? Can I do that? Can I learn from others in terms of their toxicity studies or improving the ADME properties? Can I, when it comes to the material sciences, you're getting a sense of increased physical properties as well. But one thing that's really hit home is the idea of putting purposes and technologies upon here. So what you're looking at here is this is the same chemical space, but all that's been added here is the so here's the cosmetics code, so that's A01K. So everything which has this code has been shown to be for use within the cosmetic space. And over here, you have got anti-neoplastic compounds. So you're getting a sense that actually this compound can actually be optimized for particular purposes based on the direction of chemistry that you want to go into. You can make specific tweaks to actually improve that. So the idea is that actually when you're looking at this kind of information, can you then select and then target it? Save it, go in and do your own analyses. And this is where the real advanced work goes in and the real customer centricity that we've been hearing. When you're working with companies, it's the same thing that I've been hearing. It's trying to understand what the main problems are and actually tackling it. When people are reading through a journal, reading through a particular patent, and it has 1,000 chemical compounds, we all know that's not all 1,000 are actually being in use. There's 1 or 2 that are actually the potent ones. How can we figure out which are those particular chemical compounds? And everyone has their particular process. But the beauty is that the human memory capacity cannot reach the level that a computer does. So we've now developed the ability to take all those 1,000 chemical structures, extract what the most frequent, meaningful chemical structural parts are, and then from that extrapolate and figure out which of those compounds has as many of those meaningful parts as possible. That's as close to SAR analysis within a patent as anyone has gotten. The same thing has been said with projects that we've been doing in terms of extracting the example sections out of all patents, such that if you're looking at a particular chemical, if there's one thing that I keep hearing from my customers is, no one really wants to be reading patents and journals. You have a particular chemical compound, take all the information out, the examples of the synthetic routes, the examples of the uses, take all the claims out, and allow me to flick through and go through each one, so I don't have to keep flicking through each individual journal. So this is really the start. I've given a sense of the vision, but really this is really the start of where we're sort of moving towards, and that's really working with companies like yourselves. So just to summarize, what does democratization of chemical big data provide? And this really goes towards the positive impacts that this industry has to the world that Frank was mentioning in his talk. is the fact that if you're able to get from idea development to product quicker, of course your revenues increase based on every month of extra product sales. The costs go down for every month of R&D that's required in regulatory approval. The risk of you losing the IP rights that you and your scientists have been working on then gets de-risked. But most importantly, you're able to introduce your innovative products much more faster and faster. You're able to innovate faster as well. And it only comes when we have that collaboration. We have that collaboration between listening to what the industry really needs, the real pain points that it's suffering, and trying to move towards that. So yeah, two things. Would love to speak to as many of you as possible. My card's outside, and at 3 o'clock, I believe, we have got beers and soft drinks for everyone. So that's our form of bribery. Yeah, thank you very much, and welcome any questions.